All right, everybody, welcome back. Today we're going to be talking about free fall. And this is kind of the first physical law of nature that we're really going to be talking about that's invisible and everything like that. So I'm pretty excited, all about gravity. So, a great way to think about free fall is an object is in free fall when the only force acting on it is gravity. So, when you're throwing it up, as soon as it let goes of your hand, it's in free fall. If you drop something, as soon as it's let go of your hand, it's in free fall. So, when the only thing touching it is gravity, it is in free fall. And a key thing I want to know about this chapter or this part of the chapter is that whenever we're talking about an object in free fall, we're assuming there is no air resistance. Unless it specifically says to consider air resistance, which it won't, do not think about air resistance. We're assuming that everything is in what we call a vacuum where there is no air. Okay? All right, let's continue. Okay, all unsupported objects fall towards the Earth with the same acceleration. The acceleration due to gravity is negative 9.8 meters per second squared. We say negative because it's going to be pointed downwards or towards the center of the Earth, which is always down from our perspective. We will be using negative 10 meters per second for simplicity's sake. Look, so I know it's not acceleration of gravity is primarily around negative 9.8 meters per second squared. However, I feel like students actually understand physics better and things are way easier if we're just going to use negative 10 instead. So that's why we're going to do that. And I think that'll become more apparent as time goes on. So whenever gravity is the only force touching an object, its acceleration is negative 10 meters per second squared. So again, this is a key piece of information. Whenever gravity is the only force touching an object, its acceleration is negative 10 meters per second squared. And I guess if we're on Earth. But if there's ever a question that's asking you what is the acceleration of the object at this point, and I want you to ask, is gravity the only thing touching it? And if the answer is yes, and we are on Earth, or we're assuming we're on Earth, you should be putting negative 10 meters per second squared is the acceleration. Okay? Unless otherwise stated, all problems in physics class assume that you do not take air resistance into account. Okay, so let's look at this image to the right over here. We have this person here, and this person drops a ball. When he first drops the ball, we see that it is not moving. Okay? It drops and for a moment it's not moving. 1 second later, since it's accelerating at 10 meters per second squared, it's going to go 10 meters per second. We learned about this with accelerations. 2 seconds from when it was dropped, it's going to go 20 meters per second. Because remember, every second is getting 10 meters per second faster. 3 seconds later, 30 meters per second. 4 seconds later, 40 meters per second. 5 seconds later, 50 meters per second. So every second, it's getting faster, 10 meters per second faster. Okay? And I hope that makes sense. Okay, let's do some problems. A rock is being dropped from a bridge, and it takes 5 seconds to hit the water. Out of the options given, at what point is the rock going the fastest? After the first second it was dropped, after the third second it was dropped, right before it hits the water, its speed is the same throughout. Okay, its acceleration is the same throughout, but its speed won't be. It's getting faster and faster as it falls into the water. Okay? Uh, and we could quantify this. After the first second it was dropped, we know that after the first second's drop, it's going to be going 10 meters per second. Third second, 30 meters per second. And this one gets a little tricky right before it hits the water. And you might be thinking, oh, if it hits the water, isn't it going to be going 0 meters per second? But no, don't think like that. If it's hitting the water, if it's hitting the ground, it's going to hit the water, it's going to hit the ground with a certain speed. And if it takes 5 seconds to hit the water, we should be knowing that it's going to be hitting the water at 50 meters per second. So this is the correct answer. Okay. Okay, let's look at this. A math example. A rock is dropped from a bridge. What is its speed and velocity after 2 seconds? Okay, so again, we want to be underlining key pieces of information. And it almost seems like we only have one key piece of information, 2 seconds. Like, how are we going to do this if we only know that this rock is going to take 2 seconds to hit the ground? Oops, 2 seconds. Okay, well, let's write down key piece of information that we know first. T is equal to 2 seconds. And then you might be thinking, okay, what else do we know? And then it's like, oh, okay, a rock is dropped. Okay, dropped meaning the initial velocity is equal to 0. Okay. And then it's like, okay, what else do we know? It's like, oh yeah, the acceleration of gravity is equal to negative 10 meters per second squared. Okay, and I'd always just start out with that when it comes to free fall problems. I'd start out with that because that's always just going to be the case. Okay, whenever we're doing free fall problems, the acceleration is negative 10 as long as we're on Earth. Okay, so what is its speed and velocity after 2 seconds? So I'm going to just do velocity final. That's what we're looking for. Okay, next, let's look at the acceleration formula. Acceleration is equal to v final minus v initial divided by time. And we're looking for a v final in this instance. So I'm just going to go through it. We should know the v final formula, or we can manipulate it, is equal to v initial plus acceleration times time. And now let's plug that in. V final is equal to v initial, which is 0, plus acceleration, which is negative 10, times time, which is 2. And we should get negative 20 meters per second. So that's the final velocity. The speed is going to be equal to 20 meters per second, because remember, speed does not care about direction, it just cares about the magnitude. Okay. Hope that makes sense. And we'll be doing a lot of problems, so it'll make sense over time, I believe. Okay. A cat steps off a counter and hits the ground 0.8 seconds later. With what speed and velocity does the cat hit the ground? Okay, so again, that's kind of key, uh, important piece of information, 0.8 seconds. And we'll say steps off. Okay. Again, when we're doing this, we want to always start with acceleration. It's like, okay, free fall problem, negative 10 meters per second squared, just right off the bat, free given variable. And that's like, okay, time, 0.8 seconds. And then we're stepping off, so again, initial velocity of 0. Again, we're looking for the speed and velocity. So I'm just doing velocity final. Again, I want to just say, does it hit the ground? It's like, oh, it's going to hit the ground at 0 meters per second. It's like, it's a very, it's a thought that many students have. But no, it's going to be hitting the ground at a certain speed. If it hit the ground at 0 meters per second, that means, like, if we jumped off a cliff and we hit the ground at 0 meters per second, that means we wouldn't feel anything at all. Okay, because we hit the ground at no speed. But we're going to be hitting the ground at a really high speed if we jumped off a cliff. Okay, now let's keep going. Okay, acceleration formula. Velocity final minus velocity initial divided by time. Again, we're looking for the final velocity, so we're manipulating that. Okay, final velocity equals the initial velocity, which is 0, plus acceleration, which is negative 10, with time, which is 0.8. And we have negative 8 meters per second. That is the final velocity. The speed is just going to be 8 meters per second because just the magnitude. Okay? All right, let's move on. A ball is thrown straight up with a speed of 30 meters per second. What is its speed and velocity after traveling up for 2 seconds? Okay, I'm going to show doing this two ways. Since this is a math example, I am going to show the math way of doing it, but then I'm going to show you the conceptual way of doing it, which is really important and will help a lot more. And it's a way of double checking as well. So a ball is thrown straight up with a speed of 30 meters per second. What is its speed and velocity after traveling for 2 seconds? Okay, and I guess I want you guys to just think about this. If this ball is being thrown straight up, what is happening to the ball as it's going up? You should be knowing that as it's going up, its velocity and speed should be decreasing. Okay, so anyway, that's just something to keep in mind. Okay, let's write down the important piece of information we know. At the beginning, it's being thrown at 30 meters per second. Oh, I should have started with acceleration. Again, it's in the air, so it's negative 10 meters per second squared. Okay, whenever it's in the air, whenever we're talking with free fall problems, we should almost always just start with that. And then we know time is equal to 2 seconds, and we're looking for what the speed is after 2 seconds and the velocity. Okay, acceleration equals v final minus v initial divided by time. Acceleration, oh, whoops, not that. Okay, now we're doing the speed after 2 seconds. So v final is equal to v initial plus at. Final velocity, initial velocity is 30 this time, plus a, which is negative 10, and time, which is 2. So this is going to actually be giving us 10 meters per second. Okay, that's the final velocity. And I want you to think about that. If the final velocity is positive 10 meters per second, does that mean it's on its way up, or does that mean it's on its way back down? And we should know what that means is it's actually still on its way up over here. Okay, somewhere over here. I don't know where. And the speed, again, is also going to be 10 meters per second. Okay, that's the math way of doing it, but let's talk about the conceptual way of doing it. Again, we should know the acceleration of gravity is equal to negative 10 meters per second squared. So if something is thrown at 30 meters per second, we should know, and it's thrown up, and acceleration is going down, we should know that every second it's going to be getting 10 meters per second slower until it starts going down. So at time equals 0, it's going 30 meters per second. But as time equals 1 second, it's going 20 meters per second. As time equals 2 seconds, which we just solved for, it's going 10 meters per second. And at time equals 3 seconds, it's going 0 meters per second. And then it's going to be going on its way back down. Okay. Anyway, just something to think about. We'll be doing more problems to hopefully that makes sense. Okay, let's move on. A rock is shown straight up with a speed of 50 meters per second. What is speed and velocity after traveling up for 2 seconds? Again, you could do this conceptually or mathematically or both just to check your answer. But since this is a math example, I am just going to show the math side. Okay, doom, straight up. Okay, acceleration of gravity, negative 10 meters per second squared. Initial velocity, 50 meters per second. Time equals 2 seconds. What is the final speed? Okay, v final. Okay, I'm just going to be writing down that formula now. I mean, I think we should be pretty used to this at this point. Final velocity is equal to the initial velocity, which is 50, plus acceleration negative 10 times 2 seconds. So this is going to be 30 meters per second. And again, I want to be asking, after 2 seconds, is it traveling up still, or is it traveling down? And you should know that it's traveling up because it's a positive 30 meters per second. It's not on its way back down yet. Whoops, sorry. Yep. Okay, let's move on. A rock is thrown with a speed of 30 meters per second, straight up in the air. After the rock has been in the air for 4 seconds, what is its motion? A, going up. B, at its peak. C, going down. D, it's already on the ground. So again, this is a conceptual example, but you can actually try to do this mathematically. And if you do it mathematically and you get a negative answer, you should know that it's going down. But if you get a positive answer, you should know that it is going up. Okay? So if you want to double check your work, you could do that. But I'm just going to be doing it conceptually because that's what the problem is. And we should know that every second it's changing by 10 meters per second. So at first second, and then t equals 1, t equals 0, t equals 1, t equals 2, t equals 3, and t equals 4. At the moment it's thrown, it's 30 meters per second. And the next second, it's going to be going slower because it's going up 20 meters per second. And remember, acceleration of gravity is down. After the second it's going to go 10 meters per second slower, so this is going to be 10. After the third second, it's going to be going 10 meters per second slower, which is actually 0, meaning it's reached its peak here. And after 4 second, it should be something like over here, going down. And it's going to be going negative 10 meters per second. So it should be going down. Hope that makes sense. Okay. A woman is on a bridge and throws a rock straight down with a speed of 20 meters per second. What is its speed and velocity after traveling down for 1.5 seconds? Okay, a little bit different here. This one is a little tricky. Let's see if we got it. Acceleration of gravity, always good to start with that. Free thing. Time is equal to 1.5 seconds. Okay, a rock is thrown straight down with the speed of 20 meters per second. So we should know that the initial velocity is actually going to be negative 20 meters per second. And again, what we're looking for is the final speed and velocity after 1.5 seconds. Okay. The acceleration formula. Again, we're going to manipulate that to find the final velocity. And we should get final velocity is equal to the initial, which in this case is negative 20, plus the acceleration, which is negative 10, times the time, which is 1.5. So this is going to equal, what is that? Negative 35 meters per second. Okay. And the speed should be equal to positive because it's just the magnitude. Okay. Moving on. Okay, it's a video. All right, let's do some conceptual examples here. A ball is thrown straight up. At what point is it moving the fastest? At what point is it moving the slowest? Okay. So, moving the fastest. That could be a little bit tricky. You could, most likely, people are thinking about 2 points. They think about, it's probably moving the fastest right when you throw it. But another thing someone might be thinking is like, it might be going the fastest right before it comes back. Okay. And for this problem, we are assuming that it is being thrown at level ground here. So at what point is it moving the fastest? So it's actually going to be both of these. As the ball lands, it is moving the same speed that is moving when it took off from the ground. So when it's thrown, it's moving at exactly the same speed from when it reaches that same point. However, one's going down and one's going up, but the speeds are exactly the same, again, without air resistance. At what point is it moving the slowest? We should be thinking it's going to be moving the slowest at the top. It stops momentarily and has a velocity of 0. So at the very top, the velocity, not the acceleration, the velocity is equal to 0 for a moment. Okay? Okay, let's look at this. A ball is thrown straight up. Does it take more time to go up or come down, or is it the same? Okay, so the answer is it takes the exact same amount of time to go up as it does to go down. So if it went up, it took 5 seconds, it's going to take 5 seconds to go back down. Okay, pretty much what's happening is either both sides of these are going to be looking exactly the same, except one side is going to be like going up and one side is going down and being negative, but it's going to be looking the same. Okay, if it took 10 seconds to go all the way up, it'll take 10 seconds to go all the way down. Okay. All right, and this is just kind of some example. If it's thrown at 5 meters per second, it'll be negative 5 meters per second on its way back down at the same point. At this point, it'll be going slower, 3 meters per second. But over here, it's getting faster and faster, going down negative 3 meters per second. This side, 1 meter per second, 1 meter per negative 1 meter per second, and so on. If it takes 0.5 seconds to go all the way up, it'll take a complete second to go from where it started to where it ended. Okay, so just a little bit of notes. All right, let's continue. All right, so this is another formula that we're going to be using with this part of the unit. When an object is dropped from rest and undergoes free fall, you can use the following formula to find the distance it has fallen. Okay, distance is equal to 1/2 acceleration of gravity, which we should know is negative 10, times how long it was falling for, the time, squared. Okay, and so this is that formula to find the distance it has fallen or the displacement it has fallen. And then we could use that also to find the time. This way it's manipulated so that we can find time. All right, so let's do some problems involving this, I believe. Okay, that's interactive. Okay. All right, everyone, let's look at this next example here. Take a cliff jumper steps off the ledge and takes 2 seconds to hit the water. How high was the ledge he stepped off of? Okay, again, it doesn't seem like we have like much information here, but we're just gonna kind of like write everything down. Acceleration of gravity is equal to negative 10 meters per second squared. Again, we're always just doing that with free fall, so good point of thing to do. Takes 2 seconds. Okay, now some other things. Okay, we're looking for how high and steps off the ledge. Steps off, kind of meaning that it's going to start with the initial velocity of 0. He's not jumping up, he's not jumping down, diving into it, just stepping off. And what we're looking for is how high. Okay, so I'm thinking that it's the distance or the displacement. Okay. All right, so now let's do some problems here. So let's see, we're looking at the distance formula for free fall, 1/2 acceleration of gravity times time squared. Okay, so let's figure this out. 1/2 acceleration of gravity is negative 10, and the time is 2 squared. Okay, so I could kind of do this in my head. This 2 squared is equal to 4. 4 times 10 is equal to negative 40. Negative 40 times 1/2 is equal to 20. So we can have negative 20 meters. So what this means is this person is going to be falling from a height of 20 meters. Okay, if it took him 2 seconds to hit the ground. Okay, so how high? I'm not going to put negative 20 because a height isn't ever negative. So I'm just going to put height is equal to 20 meters. Okay, let's move on. A rock is dropped from a bridge and hits the ground 4.2 seconds after. What is the height of the bridge from the surface? Very similar. Especially if you did this last problem, I'd highly suggest pausing the video and trying to do this one on your own. But anyway, here we go. 2 seconds dropped. All right, let's move on. The height. Okay. Acceleration of gravity, negative 10 meters per second squared. Time is equal to 4.2 seconds. Initial velocity is 0, and we're looking for the height, which gives us from the distance. Distance is equal to 1/2 acceleration of gravity times squared. Acceleration of gravity is negative 10. Time is equal to 4.2 squared. I am going to use a calculator for this one. Okay, 4.2 squared times negative 10 times 0.5, and we get negative 88.2 meters. However, the height I'm going to put as 88.2 meters. Okay. All right, moving on. A conceptual example here. An object is dropped from a cliff. It takes 2 seconds to hit the ground. In those 2 seconds, in which second did the object travel further? Travel further during the first second it was in the air. It travels further during the second second it was in the air. C, it traveled the same during both seconds. D, it's impossible to tell. So let's just kind of first just draw this. Let's say we got a person here. He's on a cliff. Here's the ground. Drops a ball. Ball takes 2 seconds to hit the ground. Okay, so the question is, compared to its first second, it uh did it go further? So I guess if it went further, like it'd be like during 1 second, and then this would be the second second. What does it look like that? That's option A. So again, it's always good to like draw it out because like you may be thinking like, oh, what's going on? You feel so confused, but once you draw it out, it kind of makes more sense visually. B, it traveled further during the second second it was in the air. So first second was 1 second, then the second second all the way over here. Is it going to be something like that? Or option C is, did it travel the same amount? So once the first second was like this, and the second second, these two should be even. Maybe they're not exactly even, but it should look like that. which one was it, or is it impossible to tell? And we should know that it is B. And the reason why it's B is because as an object is falling, remember, it's getting faster and faster as it falls. So the first second it's falling, it's not going as fast as the second it's falling. So it's going a lot faster the second it's falling, and if it's going a lot faster for 1 second, if it's going a lot faster during the second, that means it's going to be traveling a lot further of a distance. Okay. So how that looks like is it should look something like this. The first second is going to be going something like this, and the second is going to be going something like this. Okay. All right. Another conceptual example here. Look at the diagram to the right. At what point is the ball moving the fastest? Okay. Let's just kind of look at each of these points. We should know at first when it is first thrown, it should be going very, very fast. Okay. At point B, it looks like it's almost at the top. Maybe it's still going up a little bit, but it'd be going very slow at point B because it's almost at the top. And at the top, the velocity is 0. And at point C, we shouldn't be knowing it's going pretty fast at this point, but not as fast as point A. We should know it's not as fast as point A because at the exact same point as point A, this is going to be exactly the same. It should be going the same amount as this point when it was thrown. So D is actually going to be going faster than A. But E is going to be going the fastest because at this point, it's going to be off the screen. At this point, it's getting faster and faster as it's going down. It's accelerating negative 10 meters per second squared. Okay? All right. So a ball rolls off a 1.2 meter table and hits the ground. How long does it take the ball to hit the ground? Okay, so let's look at this. It's going to be rolling off. It's going to be hitting the ground like this. We know that this is going to be 1.2 meters high, and we want to know how long it takes to roll off the ground. Okay, so doing a few things here. How long? Great. Acceleration of gravity, negative 10 meters per second squared. The distance it's going to be falling is, I know we talked about the distance as being like a scalar, but honestly, I should have said that this is more like a displacement. So displacement is going to be equal to negative 1.2 meters. It's going to be falling 1.2 meters, and I'm going to be adding that negative here as we're doing the calculations. And then what we're looking for is the time. What else are we missing? Oh yeah, it starts with the initial velocity of 0 because it just rolls off. Okay, so we should first know that the formula is 1/2 acceleration of gravity times time squared. And I did give you the formula for time, but let me show the manipulation at this point. So first, let's get rid of this 1/2 by multiplying both sides by 2. So we're going to have 2d is equal to acceleration times time squared. And then let's divide both sides by acceleration. Let me go all the way down with this. So I'm going to do 2d divided by a is equal to t squared. And then let's square root each one. So we have square root of 2d divided by a is equal to t. Okay, and that's how we got that formula. So you can always just manipulate it. You can memorize it. Or if the teacher gives it to you on your formula sheet, you could just use it. So time is equal to the square root of 2d, 2, d being negative 1.2, and acceleration being negative 10. Okay, so how I'm going to put this in my calculator, if you are struggling with that, is I'm going to be doing 2 times negative 1.2 first, then click enter, and then I'm going to divide that answer by negative 10. Great, and then I'm going to find the square root of that. Okay. And then I actually find that the time is 0.49 seconds. Okay. All right, let's do it again. This time, I think I'm just gonna do a little shorter. A penny drops from the top of an Empire State Building, which is 380 meters. How long does it take for the penny to hit the ground? With what speed does the penny hit the ground? Okay. Part A. Let's see. Boom. 380 meters. We're looking for the time it takes to hit the ground. Okay, acceleration of gravity is equal to negative 10 meters per second squared. We have the initial velocity, it's dropped, is 0. What else do we have? We have, the distance is going to be falling, negative 380 meters, and we are looking for the time. Okay. All right, so let's figure this out. Again, I'm not going to show how to manipulate the formula. If you want to look at that, go back to my last example. But we should know that the time is 2d divided by a. So time is equal to square root of 2d, 2 distance being negative 380, and acceleration being negative 10. So let's put that in my calculator. So 2 times negative 380 divided by negative 10, square root 8.72. So it's going to take a penny 8.72 seconds to hit the ground with no air resistance. Okay, next question here. With what speed does the penny hit the ground? Okay, so I guess I'll just do everything again. Acceleration of gravity is equal to negative 10 meters per second squared. We have the initial velocity as 0. We have the distance as negative 380. And we have the time as 8.72 seconds. And what we're looking for is the speed it hits the ground. So the final velocity right before it hits the ground. Okay, and this time I'm going to be using, we have a lot of information here. I'm going to be using the acceleration formula, velocity final minus velocity initial divided by time. And I'm going to manipulate that. Velocity final equals v initial plus at. So initial velocity is 0 plus acceleration, which is negative 10. Time, which is 8.72. And we should know that it's going to hit the ground with a velocity of negative 87.2 meters per second, or the speed is going to just be 87.2 meters per second. Okay. All right. I hope that all makes sense. That is free fall. We're going to be doing some challenge examples next time with free fall. So anyway, I hope to see you for that. Thanks for watching, everyone.